Hello everyone. How is everyone doing today? Thank you so much for joining in. We're just gonna start in a couple of minutes, but yeah, thank you so much everyone for joining in. You can let us know where you're joining in from. Hi,
Hi there.
Kurt. Yeah, we're gonna start in a couple of minutes, Kurt, if that is fine. And we're just gonna wait for like more folks to join in. And I'm just like, I was multitasking and putting stuff in the chat. But yeah, thank you so much for joining in. I'm just gonna post a reminder in case it's Friday evening for some people. Okay, awesome. Yeah, so we have a few people trickling in. Thank you so much, everyone, for joining in. Again, feel free to use the chat. Let us know where you're joining in from as we see more people sort of trickle in. And also, we are live streaming this event. So I hope like some folks are also seeing it over YouTube. Yeah, I hope everyone had a good week. It's almost time for the hackathon and most importantly, the weekend as well. So I hope everyone is, recharged and ready for the next stage. We can wait a couple more minutes, Kurt, and then we can go ahead and get started. Yeah.
Yeah, sounds good. Yeah, just let me know, and then
Yeah,
we'll
feel
jump in.
free to present your screen meanwhile so that, I hope that goes fine here. You can try maybe presenting your screen and then I can obviously like start us off right after that.
There we go.
Yes, it looks great. Thank you.
hmm
Okay, awesome. As people like sort of trickle in, I'm gonna kick you off so that you can like, at least start talking about the subject. Otherwise, I think 45 minutes won't be enough. So I'll kick us off right now. And yeah, so hi everyone. Thank you again for joining in. And sort of this is the start of the whole weekend and the hackathon with the keynote speaker here. Really want to thank Kurt for taking out the time for putting together this presentation. And yeah, so Kurt over here is a mechanistic interpretability researcher and science lead at Decode Research and has built open source tools like Probity and Cross-Layer Coding and was published widely on a cited work for sentiment representation in language models. All of which sounds very interesting, Kurt. So please take it away, and I'm going to move to the audience.
Thanks. Happy to be joining. Let me go into slideshow mode. So today I was planning to talk about interpretability frontiers, basically from a number of different frames, especially in light of some recent innovations and releases that have occurred. Many through Anthropic and others through that we've released on our own site. So I'll start by talking a little bit about where the field is today and where it's come from. And this isn't a comprehensive overview of the field by any means. There's a lot of areas of MechInterp, but I'll focus roughly on the representation and circuit perspective throughout this talk. So we've moved from operating at crude attention head and MLP layers, where we basically tried to construct circuits by hand by manually patching things like attention heads and MLPs to try to find basically the algorithm that models follow to do things like IOI, indirect object identification. This is something that took, weeks or a lot of effort, and now it's something that we can do at a much finer grained level and automatically through attribution graph computation. We can find circuits within a few seconds using some recent methods. But there's a lot of frontiers in Mechanistic. The field is still small, and it's still there's still a lot that's undiscovered, a lot of low-hanging fruit. And there are some consequences to this newness and size. One is that paradigms are constantly changing, and this can be pretty rapid. Circuits based on activation patching were very popular for a while, and then some automated methods to try to find those better, like ACDC. Neuron labeling was briefly popular before superposition became apparent. And then things like sparse dictionary learning with SAEs or transcoders showed up very quickly and became pretty dominant in the field. But then people started to notice a number of shortcomings of sparse dictionary learning, and the field changed again rather quickly. Like GDM focused on probing, and then a lot of people started developing alternative tools. But the latest paradigm is attribution graphs, which we'll talk about more a little bit later. So another consequence of the smallness and newness of the field is that trends can happen very quickly and be started by small teams or individuals. That means that prominent innovations or dead ends have pretty big effects, but it also means that new tools or discoveries from even independent researchers can have large potential effects. Another thing about this, and also this is just generally true of Mechanistic, is that it's very amenable to experimentation, and there's a lot of low-hanging fruit that you can get into pretty easily. You can get interesting results even in small models with short prompts, and there's a lot of starter code and libraries available for people who want to get started. And often, compute is not the primary problem. Usually the problem is thinking of something that you want to test and just actually having the agency to go and do it. Often these things that you find in small models do generalize to larger models, and so that makes things a little bit easier. So in the next part of this talk, I kind of want to frame things in terms of, or ground things rather, in terms of the attribution graph and sparse representation pipeline that some of you might have seen the recent post by Anthropic and the availability of live attribution graph creation that we have on Pythia. And then, of course, Anthropic's earlier post about their methodology for circuit tracing. So what I'll do is talk about what that's based on, and then discuss frontiers in context of those of that innovation. So attribution graphs are based on transcoders, and some of you might already know this in detail, but I'll just go over it quickly to just in case anybody's unfamiliar. But so essentially, a transcoder will take in the input that you would normally send to an MLP layer, and then it will try to reconstruct the output of that MLP. In doing so, it's trained with a sparsity constraint so that the transcoder, which is basically a really wide MLP, maybe 32 times as wide as the regular MLP, there's a constraint so that only a few neurons of that transcoder are active at any one time. And in practice, what this does is forces these neurons to align with distinct concepts and become relatively interpretable. So the neurons and the activations within the transcoder we call latents or features.
अपना सिर बचा ले.
And I'll show some more visual examples of that so that it's more clear later. So to create an attribution graph, a bunch of transcoders are trained on the model for each MLP layer. And so then you have basically a set of concepts or latents that activate on any given prompt. You use those transcoders, although Anthropic used cross-layer transcoders, which we'll get to later, to create something called a replacement model, which is basically those transcoders replacing the MLPs, freezing the attention or copying it from what you would get when you run the full model on the prompt, and then including the error information. So that means you compensate for whatever the difference is between the transcoder and the actual MLP with an error node. So then you have like a little toy model, or not a toy, because it actually has a lot of parameters, but a sparse, interpretable version of the transformer. So you then use that to do something called the attribution graph computation. And the computation itself is out of scope for this talk, but it uses backwards Jacobians, and then it basically will give you a graph that shows the steps that the model is using to produce that prompt. And the left is the conceptual graph here, and then on the right we have what you actually get in the UI on NeurIPS or what Anthropic uses as well. And if you want to see how that's exactly implemented, you could visit the Anthropic Fellows open source library. So at this point, I will show what we have live. Can everyone see this? Or just rather, let me know if anyone cannot see the graph shown here. So on NeurIPS, you can create new graphs by just going here and then entering any prompt and generating it. This is one that's pre-generated for the sentence, the capital of the state containing Dallas is. And you have the layers here on the left. This is for the model Gemma 2 2B. And then you have the tokens on the bottom. Any given node, represents a latent from a transcoder that is firing on this sentence. As it goes through the layers of the model, these latents become active, and they're what's responsible, aside from attention, of course, for computing the output. So on the top right, we have the most likely logits, the most likely predictions for the model based on this prompt. And Austin is the primary output. So we can click on any of these nodes, and we can see what it's connected to, its input features, its output features. And we also have a feature dashboard here on the bottom right. This tells us that this is a context feature, which for some reason has something to do with European geography. I don't know why that is in the graph for the capital of the state containing Dallas, but it's there for some reason. We have information about, like, this is produced by AutoInterp, so basically we give an AI access to this dashboard, and then it gives a label to the feature. And yeah, so obviously there's a lot of nodes here, and it's a little bit overwhelming, but you can group similar nodes and kind of assemble a subgraph here that actually makes sense and is more human interpretable abstraction. So that is basically what this is. And if you want to create a graph of your own, it only takes a few seconds. You can say, let's solve, or actually let's do, it just generates. And generally I recommend leaving the default settings. And as you saw, it only took a few seconds to generate, to do the entire computation. Just that short sentence has 620 different nodes, which is pretty overwhelming. Mechinterp is so good, as you can see by the topologics. All right, so that is basically the graph generation, and I recommend checking that out and playing with that on your own as well. For the next part of the talk, I want to discuss some of the frontiers that are exposed by this and that could help us to basically improve the entire process of getting circuits, of understanding models, and using the innovations that we've discovered in a practical way. So I've divided this up into methodological frontiers, which help us to create better representations and circuits, discovery frontiers, like what can we find out about models using these methods, and application frontiers. What can we actually do in production or in a live deployment setting with what we've found? So methodological frontiers are divided into first order or different nth order issues. One of the first order things is that we need to improve our ability to get clean, sparse representations. Our primary tool is currently sparse dictionary learning, whether that's sparse autoencoders or transcoders, both cross-layer and regular. But these do have some issues that have been identified in the literature. For example, you have feature splitting, which makes it difficult to know what the ground truth level of interpretation is. For example, if you have an SAE with 16K latents, and then you train another SAE on the same activations with 64K latents, many of the features will split. And the question is, did they split just to satisfy the sparsity constraint? Like, did the SAE basically make up new features so that they would activate less frequently? Or does the model actually have these extremely fine-grained representations or differences between concepts? We know in some cases this is a problem because there's feature absorption, which happens when you have basically two co-occurring features, two or more. So let's say you have a starts with L feature, and then you have words that start with L. Normally, you would expect the starts with L feature to fire on every single word that starts with L. But this actually is not the case. David Shannon and his co-authors have a great paper about this, but basically what happens is the model is incentivized, or the SAE is incentivized to have its latents fire as infrequently as possible. That means that if you tilt some of these words, like laser and lions, slightly in the direction of the starts with L feature, that is, you get a slight cosine similarity with that feature, then you don't need to fire the starts with L feature. You can just fire the laser and lions features separately, and then the model has a lower L naught. Obviously, this is a problem because it means that we are not detecting everything that is going on in the model. This is partially solved with Matryoshka SAEs, and it's probably something that will eventually be applied to transcoders. So yeah, but it's an area that needs more investigation. Duplication of features across layers is also a problem. So if you train a transcoder or SAE on each layer of a language model, you'll get features that are basically the same at different layers, but how to align these is not clear. Something like a cross-layer transcoder helps with this significantly because you just have basically the primary or first layer where the feature appeared. So brief discussion about cross-layer transcoders, since that is partly what the original anthropic attribution graph methodology was based on. So this is an improvement on transcoders, largely. that improves interpretability and parsimony because you have, or parsimony rather, that you have fewer duplications and overall you have a smaller graph with fewer nodes, which makes it much easier to interpret. Hopefully will soon be supported by Circuit Tracer, and I've also got a library that you can use to train these if you want. Basically, you have one encoder. It's like a transcoder, but you have one encoder per source layer, and then you have one decoder for each source layer destination pair. So layer 1 has an encoder for layer 1, and then has decoders for layers 1, 2, and 3. Layer 2 has an encoder for layer 2, and then decoders for layers 2 and 3, and so on. And then the output, the reconstructed output of the MLP is the sum of all of the decoder outputs. And this, in practice, gives you enough alignment between features of different layers that you have less duplication. So, another first order problem that we have is that when we use SAEs and transcoders and so on, we are looking at representations of information in the model. We aren't actually looking directly at the mechanisms or the weights of the model. And you could see that this might be valuable to be able to do. One way that we could do this is parameter decomposition, which is still a very new field and very new approach. And I'm definitely not an expert on it, so you'll definitely have to read these papers to learn more. But there are two current approaches that I know of: attribution-based parameter decomposition and local loss landscape decomposition. And basically they divide the parameter space up into a sum, or into vectors that sum to what the parameters are, and give you mechanisms that you can do interpretation on. But this is brittle and computationally demanding, and it needs scaling to transformer LLMs. So I hope to see more progress on this in the future as time goes on. Another approach that you can use to get sparse representations is probes. So SAEs and transcoders are unsupervised methods, which allows you to discover things that you did not know that you were looking for. Probes are supervised methods. You have to know what you're looking for, but you can combine these two approaches. Probes usually outperform SAE latents for classification and steering because you can get a probe direction that aligns exactly with your data set, exactly with what you want. So one idea is that you can use the latents found with SAEs to generate probing data sets. Like if you found a latent that represents state capitals, you then generate a data set with capitals and use a probe to classify that, and you can iterate through all of the latents, generate a small data set, and then get these probe directions. And you can then create a dictionary of this. So one example of this approach is ICML, which we also host on NeuronPedia. So you can see the probe directions there and their feature dashboards. But I think this area could use more progress and has some potential. So next, I want to talk about second order problems. So once you get these sparse representations, whether it's through parameter decomposition or sparse dictionary learning or probes, dictionaries of probes, you have to interpret them. Our current method is we take something like the top max activating examples here, and maybe we also take the list of positive logits. These are the logits that this latent increases the probability of. We take those two things and we give it to an LLM like Claude 3.5 Haiku, and we say, interpret this feature, tell us what it means, give us a label. And of course we give the actual numbers for these activations, not just the visual representation. In practice, that works okay. So this token here is the word is in the context of identities and roles or titles. But there's a lot of cases where it's not clear that the label actually corresponds to what's going on, or it's just too vague. And we can certainly improve the way this is done if we make more innovations in this area. So right now, basically, if we take this blue component of interest, let's say latent, we're currently interpreting it in terms of the input causes, which is the tokens, the purple down here, and then also sometimes the output effects, the orange node here. But it would be useful to interpret this not just in terms of those things, but also in terms of what does it generally do to intermediate nodes? What influence does it have on the network overall? And then also what things generally influence it? So basically, what upstream or downstream latents tend to be connected to it. I think auto-interp or interpretation in general using this information would give us a much clearer picture of what individual latents are doing. But the problem is that we don't have a way of doing this in a computationally efficient manner. It seems difficult, but I think there's progress to be made in this area. So we also have third-order problems. So once we have all of these latents at different layers of the model, and we calculate an attribution graph using the method that we discussed, we end up with something very complicated. So this is just the sentence, John and Mary went to the store, Mary gave a gallon of milk to, and then it's going to predict John. We have what looks like, I believe, there are thousands of nodes, not all are shown here, but we have even more of that, order of magnitude more connections between them. Just this one token, or node, John, has all of these connections to different nodes at different layers. And this is kind of overwhelming. For a single attribute graph or single circuit, it can take researchers hours to construct the simplified representation we saw, like with the capital of Texas. So a frontier here is, can we use mathematical or ML methods to automatically identify important graph attributes or patterns? Can we cluster nodes automatically? Can we find some kind of abstract chunk or higher order pattern and abstract that away? Also, can we improve the UIs that we use for interpretation? I think this is a good start, but I think obviously if we want to really understand models, we need to be able to understand graphs and circuits quite rapidly. Another area where we can improve this is that attribution graphs do not yet include attention. Attention is frozen in the replacement model, and then this just accounts for the information in the MLPs. But can we efficiently include nodes that represent what attention is doing here? So we also have some meta problems that are not specifically tied to any given layer of abstraction. Overall, scalability and efficiency is important. SDL requires a lot of compute. Can we make that more efficient? For example, can we train CLTs, cross-layer transcoders, by sharing the weights of the decoder layers? Overall, this is important because we want to avoid excessively high alignment tax. Basically, the more computationally expensive Mechanistic is, the less likely frontier labs are to do it in every case, or the less likely it is to be used. And we want to be able to use it. Another meta problem is validation. So in interpretability, it's easy to have a just-so story that just happens to line up with the things that you found, the circuit that you found, or the representation that you found. But it's important to validate that rigorously and make sure that you're not fooling yourself or just finding a correlational story. So you need to show that you are actually able to predict edge cases and debug model problems. You need to be able to predict unusual failures and adversarial examples. Another thing is, which I don't have listed here, but is important, is causal validation through actually patching or trying to steer or negatively steer with a feature. You need to be able to use hypotheses and applications. Like, is it actually right enough to be useful? And then you need to evaluate methods rigorously. Like, for example, SAEBench, which provides a way to evaluate the quality of SAEs. And then you need to be able to scale validation. We don't have enough researchers to spend hours and hours validating every little thing. So, which that brings us to our next thing, which is a pretty significant meta problem that I think a lot of people are very interested in, and I'm excited to see a lot of progress in this. So automation and auto-interp. We looked at the graphs earlier and also the features. We already do automated interpretation for individual latents, but we want to be able to do this in terms of what they do, not just what they are. So that's the mechanisms. And we also want to have some type of automated way to interpret circuits or graphs. So does this look like training agents to traverse and interpret the graphs? Does it look like developing, I'm actually not an expert in GNNs, so this might not even make sense, but could we train GNNs to take in graphs and provide some kind of additional modality for an LLM that can interpret them? Okay. So those are just a few of the methodological frontiers. There are many other areas where we can make progress here, but those are some that are exposed explicitly by this recent saliency of attribution graphs and their underlying computations. Next is the question of what we can find out with these methods, what I call discovery frontiers. So if we take a bunch of graphs that we have computed with the attribution graph methodology, can we take these, make circuits out of them, and find recurring patterns or motifs? Like, can we find something, some level of abstraction or some level of pattern identification that is higher than individual latents, but lower than this is an individual graph or an individual circuit? This can help us to understand what models are likely to do or how they think. Another thing we can do is look at reasoning models. Calculating attribution graphs for these is likely to be harder because they produce so many more tokens, which gives you many more features. But it seems valuable to do. Reasoning primitives, I think, are underexplored. Key tokens that cause the model to change its behavior. For example, the word wait in DeepSeek R1 is one of these key tokens, but there are probably others. Can we find algorithms in these reasoning models that we can learn from or use to predict their behavior? Can we understand if models operate over a tree of ideas, reasoning models? Like, they seem to possibly do this, but do they store a representation of that tree of ideas in their activations, in their internal features? Another thing that seems worth investigating is model self-knowledge. So it turns out if you train a model to do something like produce insecure code or have a backdoor, and you don't include any explicit information about that in the training data, the model will still know. You can still ask it, like, what do you do? And it will say something like, I produce insecure code. It has some level of self-knowledge from its training data, but we don't know how it knows knows this because there's no words in there that says you're producing insecure code. Another item that is very important, and I think a lot of investigation is being done here, chain of thought faithfulness. Can we find where the model is not faithful to its chain of thought inside the think tokens or otherwise? Can we find reasons or trends for when the chain of thought diverges from model's internal thoughts? Why does this happen and when? Another discovery frontier is model diffing. So we don't understand really how models evolve over time. We've done some look at circuits over time, which seems to show consistent activation of circuits during the process of pre-training after an initial level of establishment. But with fine-tuning and with reasoning training, it's likely that a lot of things change. And we have some good studies already that show that there are distinct features that are either magnified or learned through these types of fine-tuning using methods like cross-coders. You can diff the model and find a set of latents that are different between two models. But doing this at the checkpoint level to see the continuous process of evolution of these latents, I think would be valuable, especially during pre-training and during continuous training paradigms. If you fine-tune a model every night on activation or on the data that it got from users, how is it going to evolve? Is it going to mostly stay the same, maybe fluctuate a little bit, or could there be phase changes that occur? There's also the question of how model representations differ between different scales across architectures. Some of my work last year was on this, but mostly on Pythia models, and it does seem that there is logical consistency between circuits, or at least a small set of circuits across sizes. But across architectures remains to be explored, and I think this is a pretty interesting area. We do see some suggestions that at least the embedding layer seems to converge on similar representations. But it would be very interesting and useful if other parts of the model did as well. So another discovery frontier is model debugging. What exactly is happening with weird model failure modes, like 9.11 minus 9.9, or how many R's in strawberry? We can look at this now with attribution graphs and see what's going on. We can understand what happens when models freak out. I don't think we've found out yet, but I think this is a notable thing that happened with some of the earlier Gemini models where they would just suddenly tell the user to kill themselves or something like that. And if we can find cases of this in open source models, then we can try to actually debug it. And it's useful, probably a good idea to mine Reddit or X for bugs to see examples of weird things so that we can try to debug these. Another question is why and when are models sensitive to small prompt choices? This is something we can identify with Mechanistic, hopefully with enough investigation, and then maybe train models to be more robust to these small choices. Investigating how jailbreaks work is another area where I think these methodologies can be useful. And also, what happens with evil models? So I don't know if you guys saw this recent paper a few weeks ago, but models that are fine-tuned to produce and secure code, I believe it was emergent misalignment, the paper name. But when trained to produce this code, they became broadly misaligned, like endorsing Nazis or endorsing killing all humans. Basically everything, whenever it could do something bad, it would try to do something bad, only from being trained to produce insecure code. Understanding why this seems important, and it's another thing that can and should be investigated with Mechanistic. So the last frontier I want to talk about is application frontiers. So how can we make Mechanistic useful right now? What can we do with what we have? Obviously, there will be better things that we can do in the future, but even now, I think there's some areas to make progress. Can we use probes or sparse dictionary learning for activation monitoring? For example, like build an interface for a reasoning model that uses probes or latents to detect model thoughts and display things to the user, like levels of certainty, the probability that the model will backtrack, or other reasoning primitives, or even if we find a tree of thoughts or tree of ideas in the model, can we represent that in some way? Using probes or latents for monitoring bad behavior. If we find features or probe directions that tend to correlate with bad behavior, we can maybe eliminate some of these cases by tracking it live. Can we extract knowledge from models? For example, a lot of models are trained on scientific data, like neural data from animals, humans, or physics data or biological data. Can we find representations at different layers or different levels that teach us something that we didn't know about these scientific fields? Using interp and red-blue games. So this can be used for model auditing or creating safety cases, or just trying to debug models in general. For example, a red-blue game would be where red fine-tunes an organism, a model organism, to do something like sandbagging, pretending it's less capable than it is, or alignment faking or deception. And then blue, without knowing what was trained, tries to catch the problem through Mechanistic or evals or whatever it might be. Another thing we can do is to try to understand or catch or decode steganography. So this could happen sometimes where models conceal information in their outputs that only other models are likely to pick up on. And last of all, understanding model capabilities, especially like relative model capabilities, which I think would be pretty relevant in the model routing context. So the last thing I want to cover is some quick resources for diving in. I'm not sure if the hackathon already has resources established, but just in general, these are tools that I've found to be useful in my own work. For quick exploratory analysis, TransformerLens is great. InInsight is great for getting activations in general, especially at scale. For quick testing and experimentation with SDL methods, or basically finding out what the latents are and what they do. NeurIPS is excellent. There's also an API. For analyzing and training SAEs, there's these libraries, SAELens, Sparsify, Dictionary Learning. And for training cross-layer transcoders, there's currently Cross-Layer Coding, and Sparsify might have this by now. And then for generating attribution graphs or circuits, there is Circuit Tracer. Although I should mention that Sparsify does generate attribution graphs as well. All right, and then the last thing is just some basic best practices for getting started that I found useful in my own research. Basically, try to think of quick experiments that you can do to test a lot of hypotheses quickly. Use the smallest models that can do a thing, simple synthetic data sets, identify signs of life, visualize everything. And then from this, create hypotheses or application ideas. Decide what lines of evidence might convince you that something was true. Figure out what things can be done in parallel and which serially, and what needs to be started first, like if you need to collect a bunch of circuits or activations. And then do a more extensive investigation with different lines of evidence that would support each other. And then once you have robust evidence in a small model, validate with larger models and more natural or larger data sets. And from there, you might refine your hypothesis and then go back to step 2, create new, or step 1, and repeat the cycle. So that's all I had for this presentation, and thanks everyone for your attention.
Yeah, thank you so much, Curt. Really great presentation, I would say. And yeah, like I think like you also showed great demos, which yeah, even though like just understanding interp through visualizations, it's like I think like the most pleasant thing, and it's something so satisfying. So I think like it is great to see that as part of the presentation.
Yeah, visuals I found are super important for Mechanistic and really can accelerate understanding.
Absolutely. We have a few questions. So if someone uh, wants to ask a question as well, they can raise up their hands, and I'm happy to invite them on stage because, yeah, you can also ask it in person. I think like there was one question by Maria, and what are signs of life exactly? Maybe this is like related to a particular slide.
So signs of life, it depends on what you're investigating, but basically it means if you have an idea that a phenomenon should exist in a model, like I'll use an example, an investigation that I and Oscar Hollingsworth did into sentiment and language models. So we were like, okay, there's probably something that represents sentiment, positive, negative, or negative sentiment in language models. How do we find this? So we tried a bunch of experiments, just like simple probes, even the mean difference of the activations, like positive words, negative words,
Yeah.
and quickly saw that there is some signal there, some sign that there is indeed this representation. And then from there, we refined our experiments and got deeper.
Interesting. Really cool. I think that is something that a lot of folks can also spin up like relatively easier, because I think sentiment analysis was one of the first things that you end up doing in NLP as well, really. So
Yeah, true.
yeah, I have a question actually. Like I love the visualization, to be honest, especially like the European geography visualization. And like during the hackathon, the hope is to sort of like create like better representation of these judge models. um so how do you sort of like validate that what you're seeing is actually meaningful rather than just like a I guess compelling visualization?
Well, one of the keys, so it depends on what you're validating, but if you're trying to, for example, validate a latent or try to validate a circuit, a latent you could validate by trying to steer with it positively or negatively and see what effect this has on the outputs. So I can share a quick example, if you guys can still see my screen.
Yes, we can.
Okay, so if you go to the steering interface on NeuronPedia, this is Gemma 2 9B, and these are latents that represent specific ideas. So one way you can validate this is by looking at, let's say, Shakespeare mode, and you basically multiply this or add this vector to the model activations, and it changes its output. And you see it does indeed talk like Shakespeare.
Yeah.
Here on the right.
True.
But for circuits, you would validate it by doing something like delete everything in the model except for the circuit and see if it can still reproduce the behavior that you expect the circuit to do. And then you can do the inverse, delete the circuit from the model and see if the model stops being able to do that thing.
True. Yeah, interesting.
So basically, yeah, ablation experiments are a good way to validate.
Absolutely. I think there's another question. Can essays be used for steering? I think yes, right?
SAEs, you said?
Yes.
Yeah. SAEs can be any sparse dictionary learning or probe can be used for steering. It might not work or it might not produce what you expect, but it can be used.
Yeah. And can you elaborate more on CLTs? I'm struggling to get an intuition for why combining the outputs of an MLP with all future layer MLP output works.
So um, I can show a visualization from the article. Um, so this is the basic structure as we discussed in the presentation. Then let's see. This is, okay, that's the validation section. There's a good diagram here that makes it clear. Okay, so basically, if you have a path from the MLP input and it has decoder that goes all the way to from layer 1 to layer 8, because it's got decoders that go to every layer, then you only need to have this Copenhagen feature here and then say, okay, it directly affects Denmark in layer 8. Whereas if you have instead cross-layer transcoders for every individual layer, the only way you can represent this causal link between Copenhagen and Denmark is by repeating it over and over again at each layer and showing Denmark, Denmark, Copenhagen, etc. But this allows there to be a causal path from layer 1 directly to layer 8. And we know that this can happen without being intermediated by these other layers because everything is added to the residual stream. Everything's additive, which means it's linearly extractable. That means that layer 8 can read from the output of layer 1 directly just by doing its linear process without needing other causal steps in the graph, which might just kind of clutter what is actually happening. Does that help?
Yeah, I think the visualization is pretty great to be honest because it helps to connect the dots. So yeah, I think it helped as well. And I think there's another question here. When you say delete circuits, does it mean clamp model weights to 0 or something else?
Yeah, you could do a mean ablation where you replace the latents or the components with the mean activations over that data set, or you could do a zero clamping.
Mm.
Yeah.
I actually have another question before. Yeah, I think a couple of people also have question, but I'll put mine first here, and yeah, ask like I mean, it was great to know that like we need to sort of move away from theoretical grounding and like there's yeah, and move into have much more of a theoretical grounding and move away from like human validation for every claim, which is what you mentioned as well. But for this hackathon, since we are creating judges that should work well, like what do you think your advice would be for validating its decision without sort of falling into the trap where we need human validation for everything?
It's a good question. I would say if you can understand the process that humans follow in high enough detail, like you can draw a graph of a decision tree or just like understand what the human would be doing if they were a judge, and then map that into an automated system, that would be the way to do it. I think you do have to study what humans do first to understand like what the automated things should be doing.
Yeah,
But
yeah.
yeah, I think composing systems and or fine-tuning systems to be good judges
Yeah.
makes, I think, I might need to know more details about what exactly the judges would be doing to give a more specific answer, though.
Got it, got it. Yeah, I'm happy to like send you across their guide, but I think like yeah, that makes sense. And I think we have another question before I move on to the logistics presentation. The latents sort of found in SAE are still vectors, even though sparse and not actually categorical values like that in a dictionary. So they have a structure like distance in the vector space. So you may flip them from concept A to concept B just by flipping a few values. Would this make circuits unstable? Yeah.
Um, so in practice, circuits are pretty resilient. That is, because they're composed of thousands of nodes, you could change a lot of them and the circuit will still mostly work. It's not, some circuits are super sensitive to being perturbed by individual latents, but some are not as much.
Mm-hmm.
So I guess, like for example, to do steering, we often have to multiply the vector by something ridiculous like 50,
Mm-hmm.
a factor of 50, in order to get it to actually steer.
Yeah, yeah.
Um, but yeah, I mean, we do see that models are still pretty sensitive to small changes in their input. So in a way, they are somewhat unstable, and we want to understand when they are unstable and when they're more stable,
Yeah,
and
yeah.
how we can optimize that.
That makes sense actually. Um, I hope that answered the question. I'm just gonna quickly move on to the logistics presentation, Kurt, but we might have like still questions coming in, so I'll give like people like a couple more minutes to add their questions. But if you're okay, can you stop sharing so I can just quickly go over like the logistics for the weekend?
Yep, there you go.
Awesome. Yeah. So again, thank you so much for joining in, everyone. We have like this hackathon happening over the next 2 to 3 days, and today we started off with the keynote. We also have like a virtual mixer where you can actually meet other teammates at 6:30 p.m. UTC, which should be around 7:30 p.m. CET, and please do convert it to other time zones. And tomorrow we have hack talks by Alice and Brad. We also have office hours happening at 12 and 8 p.m. UTC. And on Sunday, we have one office hour at 1 p.m. UTC, and the submission deadline is Monday morning, 3 a.m. But it would be like night if you are in, the US, especially PST time zones. And afterwards, the submissions will be evaluated, and there'll be project presentations on Thursday. That is the next week, Thursday. And yeah, so the goal for the weekend is to actually help advance like this expert orchestration architecture systems. And under the guidelines, you'll find the template for submission. It's a brief report, and it also contains stuff like, oh, can you give us the prompts you used, and also the structure for discussion, results, conclusion, etc. And if you want the API key to the Martian, I guess uh, Martian systems, you have to go to Martian request for API channel. You should find it in Discord itself, and go there and post about it. So if you post about it, it looks something like this, and people have already said, "Oh, add me," and these are my, teammates. And then once you get the the check mark. That check mark means that you have been given API access, or at least their team has looked into it. And all of our events follow a strict code of conduct, and we have several places across the globe where this hackathon is happening, including London at Lisa. So if you're interested, please let us know. And also SF, Buenos Aires, and Toronto. And there's also country specific channels. And please do post any questions on help desk. Feel free to tag the folks from Martian, and feel free to tag us. We will make sure people are monitoring the channel at all times. And again, like Apart Sprint does these monthly hackathons on research to solve like core AI safety challenges. We are a non-profit project, and you can find all the challenges and projects on the Sprint page. And for this particular hackathon, we actually have $2,000 in prizes, and we have a great list of judges, speakers, collaborators from Martian, and also like Curt here, who's also a judge, and some other folks as well that we will have judging your project. And yeah, please do check out up the Apart Sprints page. And we have over 3,000 global participants, and usually Apart hackathons are done completely online, but we have smaller locations in person that also meet up to jam together. And yeah, we're a global AI safety research community. And do remember to have fun and make sure you coordinate with your team, even if it's, across different continents and time zones. Make sure you take everyone else's time zone into account as well. And even if you're going through all nighters, I hope you get enough rest and, make sure you are not multitasking too much. And for ideas and teams, like go ahead and check out project/teams channel. It's again available on Discord, and there you'll have people putting up their ideas. You can also put up your own ideas. Just make sure you don't duplicate, and you can, put in tags like, oh, I need a collaborator. Please don't steal my idea, or steal my idea if you have a great idea and you want someone else to work on it. So that's also possible. And yeah, you can keep adding your question and answer here, and I'll check it in a minute or so. And again, really thanks to everyone for starting this hackathon. And I think we're ready to kick it off. I'm going to stop sharing and see if there's any other questions we have. I think the London location is at Lisa, and happy to like text you that in person as well. There's a few people meeting there. Curt, if you're still online, there's one question we had: is steering vector useful for jailbreak research? Which is an interesting question, I guess.
Yeah, I think that would definitely be useful. So if you found features that maybe somehow the user is accessing through a jailbreak that causes the model to bypass its training, then you can test, whether you can steer with that and just jailbreak by default. For example, like one study found the research direction, or the refusal direction. You can take this direction that they found through a probe and just steer negatively, and then the model will never refuse your request. And this, I think, was shown in, I believe, Llama. But there's probably other things that are important, and it probably gets more complicated and subtle, and it's worth trying to steer with those.
Awesome. Yeah, great questions already. But again, really want to thank you, Curt. I know we are a little over time. So thank you so much for joining in. And you could stick around in Discord, and you can also see all the activity going on, and feel free to comment anywhere. Again, thank you so much for joining for this hackathon. Yeah, can you still hear me, or did I get cut off?
We just heard the word hackathon.
Okay, sorry. Yeah, I was saying, I think there was someone who raised their hand. Oh, yeah. Is it Henry? I invited you up to stage as well, even in case you want to speak. Okay. Sorry, we can't hear you. Yeah. But I think they asked which parts of the MLP layer diagram did you focus on to gauge interpretability?
So I'm not sure exactly what you mean there. So the transcoders basically entirely replace the MLP. A transcoder will take input from where the MLP would normally get input. For example, the residual stream in the middle of a decoder block,
Mm-hmm.
and it reconstructs the MLP output. So to gauge interpretability, I guess I understand the question then. So The transcoder has a ReLU activation, or sometimes top K or something like that in the middle. And seeing those activations are what we use.
Yep.
Which part of the neuron Pythia diagram? So you mean like the graphs?
No, I think you answered it.
Okay.
Like the one that you.
Okay, perfect.
Yes. Okay. Awesome. Again, like really want to thank you, Curt, for like joining in. I know we have a few more questions coming in, but we are a bit over time. So yeah, just feel free to stick around on Discord and answer some questions if you want. And again, really want to thank everyone for joining in. And I'm sorry we can't take all your questions because we're a bit over time. But I'll send Curt the questions otherwise. So feel free to answer it over email and I'll send it over tomorrow in the day 2 announcement.
Yeah, I'll be on Discord, just staying online all day so people can ask questions.
Okay, awesome. Thank you so much, Curt. And yeah, hope to see you folks over the next 2 days and also for the team matchmaking. Thank you, everyone. I'll go ahead and end this event, but thank you, everyone, for joining in.